I will give you 2 lectures. And then I will try to talk about atmospheric aerosol basics by assuming that most of you are new to this field and considering the interdisciplinary nature of the audience. And I will tell about microphysical aerosol.
It's not
Okay. I will start with now you can atmospheric aerosol basic by assuming that you have no background in aerosols and also by considering the interdisciplinary nature of the alliates, and then tell about microphysical and optical properties which is needed to estimate the climate impact assessment. So the first 3 topics I will try to cover in the first lecture. And effective development of radiation, I will give the brief introduction to the module, and afternoon, when you go to the lab, we cannot accommodate all of you in the lab, so we will divide into 10, group of 10, and then when 10 people are in the lab, the balance, the rest of the people will be here doing tutorials on impact of aerosol radiation. And then in second lecture today morning, I will try to tell about recent advances in aerosol science and give some introduction about measurement. That will be helpful in the afternoon, your lab session. And please note that all lectures are very basic level only. And it is not a seminar, it is a training program. So please feel free to interrupt me at any time and ask questions. If you don't ask question, I will ask questions. So then otherwise there is no use of the training. See, if you have not read the recent report of Intergovernmental Panel for Climate Change, it was released in 2013, at least you might have read the newspapers. What are the recommendations? And you probably noted the observed increase in temperature during the last century, and also the predicted temperatures for 2100. So you probably know that there will be a large increase in temperature, and it is usually interpreted to carbon dioxide, increasing carbon dioxide concentration, that is believed to be the major cause of such temperature increase in the past. And in that context, there were several reports that solar radiation reaching the Earth's surface seems to be decreasing since 1950s. So it is from measurements. So it is globally about 5% reduction per decade if you take 1960 to 2000. And southern hemisphere and northern hemisphere both you observe a reduction of radiation at the Earth's surface. So at one point you have large amount of warming in the atmosphere, and on the other hand you have a large reduction of solar radiation at the surface of the Earth. So this is popularly known as global dimming, because when you look the planet from space, you will see it dimmer compared to previous time. You see 1950s and 2010, the planet had been dimmer, that is what it shows. And the question is global dimming versus warming, because it is opposite process as far as temperature is concerned. So I will tell you more detail about that later. The question is why we are concerned. So there are some reports which shows that while many parts of the world shows that brightening means the dimming has stopped and more radiation is coming to the Earth's surface. So the energy, solar energy coming to the surface of the Earth drive all the atmospheric and ocean circulation. So you know that. So it is very important. And while many parts of the world shows brightening in 1990, some region, especially Asian region, shows continuity. If you see whatever is marks shown as red is dimming, and whatever is shown in yellow is brightening. So you can see that Asian region, African region, parts of South America. This region shows Benin and Europe, US and Australia. All this region shows brightening. So if you take the whole planet, it is 10% over USA, 30% in parts of former Soviet Union, Europe 60% and 33% over India. So you can understand the magnitude of reduction. Over Indian region and Chinese region, it is very high. And dimming is a global problem. We can't ignore that because the impacts or climate impacts of global dimming can be devastating. For example, see, massive famines as a result of droughts during 70s and 80s over northern Africa. It is believed that, or model simulation shows that a large decrease in solar radiation reaching the Earth's surface have resulted in less rainfall over northern Africa. So you know land sea breeze circulation, probably monsoon circulation, general idea of monsoon circulation. If you reduce the surface reaching solar radiation from the surface from the sun, you know that land ocean heat capacity is different. So land responds very fast because heat capacity is low, but ocean responds slow. So any reduction in solar radiation at the surface will be very fast absorbed in the land compared to that over ocean. So what happens is if you reduce the solar radiation or shade the solar radiation coming from the sun, what will happen is you are reducing the contrast between land and ocean. So circulation is affected. So that is what is happening here. So the effect on Asian monsoon is because of these reasons. One is imbalance between global dimming at the surface and global warming. And one aspect you have to remember is global dimming shields the ocean from solar heat, and that means dimmer and warmer world. Any reason, due to any reason you have reduced the surface radiation, then you are going to have a dimmer and warmer world because of absorbing species in the atmosphere. And it is believed that dimming may have a detrimental impact on Asian monsoon, restricting rainfall to half of the world population. So you understand the gravity of the problem. And during the beginning of 1980s, no one was sure what causes this global dimming. So see this graph. It is showing solar radiation transmittance. It is 70, it's 100%. 100% of solar radiation is reaching the surface. That is not the case, definitely. So it is because of molecules and other constituents in the atmosphere, we will not have 100%, so it is about 94%. And see these two spikes coming below, that is reduction of transmittance up to about 75% here, 80% here. These are our two major volcanic eruptions during 1991 and 1982. And you know that when there is an volcanic eruption, large amount of aerosols are introduced into the atmosphere. So during this time, you have seen a large reduction of solar radiation because transmittance is low means your radiation is reduced at the surface. So that means you are shielding the radiation. So because of this, it is currently believed that solar dimming is caused due to the increased presence of an atmospheric species known as aerosol in the atmosphere. That is how this topic has become very much interesting to climate science community. And it is a new topic. Until 1990s, early 90s, nobody was studying aerosol except condensation nuclei, because it can act as cloud condensated nuclei. So that was the only effect. As far as climate change is concerned, it was not considered an important species. So aerosols, you can define particles of solid or liquid phase suspended in the atmosphere. And it can be considered as a colloidal system where atmosphere is dispersion medium and particles are the dispersion phase. even though they constitute a very small fraction of atmospheric mass. You can calculate the mass. It is a very small fraction of atmospheric mass. They are capable of affecting the climate system. And what is shown here is electron microscope picture of polluted air and clean air, rural and urban. You can see that large number of particles are here for unit area and very less number of. But the difference is not ending there. It's much more than that. You will see in the next few hours. Chemical composition, refractive index, like that, climate level parameters. So many parameters are there. All those things are different between polluted air and clean air. That is required for making an assessment of its impact on climate. So these are very small particles. You cannot see with the eye, but you can see their presence because of their optical effects in the atmosphere. So we can see their presence as red sunsets and sunrises for us a haze. In the red color, you know that valley scattering is the reason for blue color of the sky. And similarly, this during sunset and sunrise, red color is due to me scattering of these particles. If you need more explanation, you please interrupt me and ask. I will be glad to tell you more about it. And the size of a typical size of an aerosol is 0.5 micrometer, making it ready to be very active in the visible region of the solar spectrum. Because if you know scattering theory, if you don't know, I will be telling briefly about that in the next few minutes. Then your particle size is same as wavelength of radiation interacting, scattering effect will be maximum. So that is the one characteristic of scattering. So 0.5 micrometer is comparable with maximum radiation coming from the sun, that is green. If you plot a Planck function, I'm sure you know Planck's radiation law. So if you plot Planck function, you will see that green wavelength, you will get the maximum. So since the typical size of aerosol particle is 0.5, it is radiatively very active in the visible medium of the solar spectrum. Doesn't mean that it is not active in the IR spectrum, but comparatively its effect is more in the visible medium compared to infrared. And don't get confused with air pollution. Air pollution is different than aerosols. The air pollution, you can define as a contamination of air by toxic gases and minute particles of solid and particulates in concentration that can affect environmental health. When you say air pollution, mostly you are talking about the health, not climate actually, but it is a mixture of gases and particulate matter. And we are talking about, at least I am talking today about the particulate matter, not the gases. Because carbon monoxide, carbon dioxide, several NOx, the several gases can be emitted from the source tubular exhaust, but that is not considered as the part of aerosol. Aerosols are only particles of solid or liquid phase. Gas species is different. So water vapor is not an aerosol. It is considered as a gas. But then water vapor condenses on a particle and form cloud droplets. It is particulate, but it is not considered aerosol because it is so large. Aerosol is not only defined in terms of its size, in terms of the size, residence time also. Cloud droplets cannot stay for a long time in the atmosphere. So aerosol should stay for at least a few days in the atmosphere. Otherwise, it cannot affect the radiation or climate. So there are a lot of confusions about cloud droplets and aerosol, but we cannot exactly define the border. This is the border for aerosol or clouds. Very small cloud droplets also you can consider as aerosol if the residence time is much larger. I will explain to you what is residence time and details of that. And I will tell you why aerosols are important. It is mainly because of the effect on radiation. Aerosol can affect radiation, incoming solar radiation as well as outgoing low wave radiation. And because of that, it is important to climate. That is the topic of today's both lectures. And remote sensing, satellite remote sensing or ground-based remote sensing. Aerosols are important because if you want to derive or retrieve surface properties from satellite sensor, you need an atmospheric noise. So you need it to correct for the atmospheric effect. So you assume that you want to study about sea surface temperature from satellite data. Then atmosphere is a noise. Because satellite sensor receive both signal from the atmosphere and ocean. So you need it to separate them. So it is actually a noise. Because of that, you need to know about aerosol radiative effect if you want to derive sea surface temperature, vegetation, snow, like that, anything in the atmosphere. On the other hand, if you want to study the atmosphere, then the land is a noise. Because land also, the energy is reflected or emitted, so you need it to correct it from that. So that is not the topic for today's lecture. And then agriculture. See, there are several reports that aerosol scattering and absorption decrease the surface reaching solar radiation. I already told that solar dimming is because of aerosol. So any reduction of radiation at the surface will have an effect on the crop yield. That is one inference some investigations are showing. So, and there is another effect also, deposition of this particle on the leaf. That also affects crop yield. If particles are deposited on the surface of the leaf, then also you have effect on reduction in the crop yield. But remember one thing, we are in tropical region. We have plenty of radiation. So you don't need all the radiation for photosynthesis. So, but the regions like China or even if you take Indian conditions, Punjab, for example, which the state which having a lot of agriculture, there may be some effect. But otherwise, tropical region, this effect of aerosol on agriculture may not be that high. And then another reason is health. You probably have read that pollution causes lung diseases and skin cancer, all those things. So that is there, but we are not into that. We study these three, but I am more focused in this, and our talk is also mainly focused on climate, aerosol effect on climate. And health effect, if you are interested, if you see regional cancer center websites, you will see a lot of information about health, how air pollution can affect health. And see, I would like to bring your attention to a few of the reports why aerosols are important. There are some influences on aerosol climate effect. So before I go to details, it may be useful for you to see some of the diagrams. Black carbon aerosol, I will tell you what it is. I did not tell you what it is, but it's a type of aerosol. Contributes to droughts and floods in India and China. And then another report says that soot is also black carbon aerosol. It is all coming from biomass burning and transportation. And soot blocks sunlight and itself is reducing crop yields. And soot intensifies flooding and drought in India. And then one study says that, see these two studies, aerosols slow down hydrological cycle and reduce rainfall during monsoon. But same year, another study says that aerosol leads to advancement and subsequent intensification of Indian summer. So both are contradictory. It is not same. Their inferences are different. I will tell you why. I will talk about it in detail later. And this is a recent, relatively recent one. Aerosol from India's English tropical cyclone over the Arabians. And this one you probably have seen much more than any other impact of aerosol on glaciers. So we still do not know whether aerosol can impact glaciers or not. See some of the reports on that topic. Black carbon is a significant factor in melting of Himalayan glaciers. Very recent one. And another one says that black carbon deposit on Himalayan is returning as third winter. And these are all global news agencies like Science News or NASA News. So there's a lot of importance. And black carbon claimed for 30% of Nepal glaciers and 90% of Himalayan glaciers is caused by aerosol. See the thing, I am not commenting on the accuracy of this because I will be telling you other aspects of this news also. But if you see this graph, this is data on aerosol and glaciers from 1960s. So this is a term you will not understand now, but I will tell you a few minutes later. This is aerosol concentration. You assume that y-axis here is aerosol concentration. So you have seen a 5-fold increase in aerosol optical depth from 1962 to about 2007. 2010 also it is approximately the same. And at the same time, you have seen a 23% reduction. Professor Anil Pinker will be talking to you. I don't know, you have already, he has already spoke to you. He will show you about this, talk about this. But if you want to plot a scatter plot, you will get very good correlation between the two. But question is, because of a simple correlation, can you justify that this is because of this? Because many things can be correlated. So never think that if you have a correlation means that you can say that this is due to that. It's not like that. Correlation is coming maybe because of some other reason, may not be because of this. Because this decrease may not be connected with this. But you can make your own judgment at the end of today. Because I will tell you more information about this. And then this data is from RC and everyone also. And there are so many questions on aerosol climate impact. What are the impacts of man-made or unorganic aerosol on Earth's climate? That is one question. And is aerosol radiative forcing? Forcing is the effect on radiation. There is a technical term used to tell the effect of aerosol on radiative, aerosol radiative forcing. Similar in magnitude to that of greenhouse gases. If it is similar in magnitude, it will offset global greenhouse warming. If it is opposite, similar in magnitude and opposite in sign, then it will offset. Assume that it is same sign, then it will complement it to global warming. So, what is the impact of aerosol on cloudiness and rainfall? Monsoon, effect of monsoon. And can aerosol alter natural technologies? Like that, I can list so many questions which are not yet answered. So, I will give you more information about this aerosol by assuming that you don't know anything about atmospheric aerosol. See, you can have natural or man-made aerosol. Man-made aerosol is called anthropogenic aerosol. And if you see the natural aerosol, soil dust, sea salt, volcanic dust, and sulfate from oceans, all constitute accept aerosol. At the same time, you have industrial emissions, automobile emissions, biomass burning, all can produce man-made aerosol. So the question is cooling or warming. What is the net effect of aerosol? That is the most fundamental question which we are trying to answer. Whether it will lead to cooling or warming, because that is very important. If it is leading to cooling, that means part of the global warming is offset. If it is leading to warming, then it will add to the warming. That's not a good news. So different aerosol having different characteristics that determine the climate impact finally. And this is a typical size of an aerosol. This scale is 1 micrometer, and if you see the size of the particle, you can have large particle which is larger than 0.1 micrometer and fine particle which is less than 0.1. So the typical size is 0.5 micrometer, I already told you, and depending on the size, you can divide into 3. See, fine, large and giant, and different size range having different importance. For example, fine aerosol 0.001 micrometer to 0.1 micrometer in size, and large aerosols are 0.1 to 1 micrometer in size, and giant aerosols are 1 to 100. And for atmospheric radiation and optics, and hence climate, it is 0.1 to 1 micrometer. And for cloud physics, anything above 0.1 micrometer is important, because very small particles cannot act as cloud condensation. Only particles above some size can act as cloud condensation. And for air chemistry, that is air pollution, all this size range is important. So you note down the different size ranges, and it is important. 0.1 to 1 micrometer is important for atmospheric radiation and optics because of the reason I have told you. It is radiatively active in that same wavelength. When wavelength is same as size of a particle. So this is the region where you have maximum amount of energy from the sun. And then if you take the force strength, you can see that 30% is coming from the ocean, and then large amount, that is 38%, is coming from deserts, and small fraction is coming from biomass burning and automobiles, and industrial emissions contribute to about 24%. So the main point you have to remember is, on a global basis, natural aerosol abundance is several factors other than anthropogenic ones. So why we worry about anthropogenic aerosol? Because natural aerosol you cannot control. It is coming from ocean or deserts. There is no control is possible. So we can control only anthropogenic aerosols. And that is the topic. Anybody talk about, you have seen from the news and the title I have shown you. It is all anthropogenic aerosol. Nobody is talking about natural aerosol because you cannot control them. Even if you study, you say that it has a very bad effect. Nobody can control them.
So how is ocean contributing to
I will tell you in a few minutes. I have a detailed description of production mechanism. So that is one question you should ask yourself. Then why we are, see the thing here, industrial emission and this one contribute only 24 plus 8, 32%. So the rest is natural. So almost 70% is natural aerosol. So all intergovernmental panel for climate change and all other agencies are mostly interested in this 30%. Why? The reason is there is no direct relation between aerosol mass, optical properties and radiative properties. That is the reason. The 8%, this is mostly black carbon, which I said before. I will tell you more about it later. And it is coming from biomass burning and automobile emissions. And 8%, by today afternoon, you will be able to calculate yourself how much effect of each aerosol to the radiation. Climate impacts we may not be able to tell you in a day, but the purpose of afternoon tutorial is to show you how you use a calculator. You have a calculator in your mobile phone. With that, you can make an assessment of aerosol on radiation. That is the purpose of the tutorial today. So you yourself will be able to convert this 8% into optical properties. So the most fundamental optical property is aerosol optical term. I will define it later. If you convert it, it will go to about 15%. And if you convert it into climate effect, that is radiation, how much effect is this 8% can lead into surface leaching radiation? It will go to 60%. So that 30% anthropogenic aerosol may contribute to 80% in radiation effect, and 20% only is natural aerosol. So that is the reason. So because often people get confused why this is a small amount and why everybody is talking about that. And there is no direct relation between those quantities. And climate effects are determined by its optical properties. You can imagine. See the sea salt aerosol here, it is a purely scattering type. So it can only scatter. So scattering is only a redistribution of energy. It is not like absorption. If you are physics background, at least up to degree level of approach standard, you know that scattering is only redistribution of energy. Not energy is not lost anywhere. So you cannot lead it to a warming. So it is a cooling agent. So anytime when you see a scattering type of aerosol, you can believe that it is a cooling agent. And black carbon aerosol, it is a highly absorbing type. If you illuminate a medium dominated by black carbon aerosol, then 23% is scattered and 77% of the radiation is absorbed by the medium. So where that 77% will go, it will be utilized to warm the medium. So if you are talking about atmosphere containing black carbon aerosol, 77% of the radiation will be utilized to heat the atmosphere. So that is how it contributed to the warming of the atmosphere. And there is another one, dust aerosol coming from desert dust, and that is partially absorbing. It is only having 12% absorption and 88% scattering. So its net effect, see the effect when you say completely scattering type means it is a cooling agent. But completely absorbing aerosol means it is a warming agent. So when you calculate the net effect, it is the net effect between scattering and absorption. Cooling versus warming. So here definitely it is a warming agent, but here we cannot say because 88% scattering is there. Similarly, sulfate, anthropogenic sulfate is a scattering type. So it is also leading to cooling. So if this much you remember that scattering type aerosol leading to cooling and absorbing aerosol leading to warming, then you will be able to follow which I am trying to say. Because this is our one semester course, we are trying to put it in 2-3 hours. So there are so much constraints from my side. But you have tea time, lunch time, and today there is a dinner also. So whenever you need, you can ask questions or most welcome to ask in the seminar also. And this is the most important aerosol, black carbon. See the one thing you have to note is that largest sources of black carbon are Asia, Latin America, Africa, China, India together. Account for about 50% of global black carbon emissions. So that point you keep it in mind. I will not want to talk to you about policy. It is a very important statement when we talk about international policy on climate change. But just remember that I will use it later. And see the sources. You can have extraterrestrial sources and terrestrial sources of aerosol. Extraterrestrial sources is coming from meteors and carbon, that is a very small fraction, so I am not talking about that. The terrestrial sources you can divide into natural and anthropogenic. And both natural and anthropogenic aerosol can be formed because of mechanical disintegration and gas to particle conversion, two processes. I will tell you very briefly about that due to limitation of time. And once they are formed in the atmosphere, it can be removed due to this process. Its density is larger than that of atmosphere, so gravity has a role. So gravity is it will fall down. If an aerosol particle is formed in the atmosphere, it will fall down into you can calculate. I will give you a simple equation. If you want to calculate, you can calculate how much time it will take. You take a particle at 3 kilometers of some particular size and then calculate. Assume that there is no winds. You take how much time it will take to reach the surface and get removed. And then rain. During rainy season, large amount of particles will be settled because of rain washout and clouds. As I said, aerosol can act as cloud condensation nuclei, and in that process, it will be removed from the. This is the simple equation you can use to calculate the fall velocity of an aerosol particle. fall velocity and diffusion coefficient, these two are basic parameters which determine the gravity settling rate. And for particle much larger than air molecule, fall velocity is given by G, where B is the particle mobility defined as velocity per unit driving force. Driving force here is mg. And we calculate the mobility from diffusion coefficient and the temperature. And remember, particle mobility decreases as air molecular density increases. So, at lower atmosphere, since molecular density is more, mobility is less. And the molecular density is less and mobility is more. And in the fall velocity is directly proportional to the particle mobility. So very low levels of the atmosphere, fall velocity is less compared to that to the surface, because atmosphere is dense close to the surface of the earth. So the fall velocity is less. And if you calculate using this equation, this is what you get. You have a 5 micrometer particle and 1 micrometer particle. So this is the fall velocity. The fall velocity as a function of altitude. At 25 kilometers or 20 kilometers, the fall velocity is very high, but it slows down when you approach the Earth's surface. You can use that equation to calculate and check yourself. And see the typical raindrop. You can see it is about 1 millimeter in size. The fall velocity is about 650 centimeters per second compared to 0.05 centimeters per second at 25 kilometers for 1 micrometer particle. So this means very less time it can reach the surface from 3 kilometers. If you calculate how much fast it can come, it will come very fast. See that calculation. So it is called residence time. How much time it can stay in the atmosphere? It is called residence time. And if you see the large aerosol and small aerosol, this is 5 micrometer particle and this is 0.5 micrometer particle. Here you have a residence time of 10 days. And small particle can stay much more in the atmosphere since its effect is much larger. Unfortunately, the particle like black hole is highly absorbing and having an important effect on climate system that can stay much more time than other aerosol types. So it is 23 days. And typical raindrop can stay only few minutes. In few minutes, it will come from 2 to 3 kilometers to the surface of the earth. And after production, particles in the radius range 0.1 to 5 micrometer are capable of getting transported to long distances as long as 5,000 kilometers. See, this is showing one example of how the transport of desert dust is happening from Saharan region. And you can see that it can actually cross the continents, one continent into another, it can get transported. And the deserts of the world produce about 22,000 teragrams. 1 teragram is a megaton, and per year of mineral dust aerosols. And over desert region, dust production increases exponentially with surface speed. If you measure the dust over desert region as a function of wind speed, surface wind speed, it is kind of an exponential function. You can get that information. And see another satellite picture. It is a satellite picture and it is showing that from this region, the Saharan region, cross Indian region and go to Bay of Bengal and Chinese region. And that is about long range transport. But this is about short range transport. If you want to study the effect of an industrial area to a residential area nearby, then you have to use aerosol dispersion. Then there are 3 factors which affect aerosol dispersion from one area to another. The first one I spoke is about long range transport. This is a very short range. And sources, what are the characteristics of sources? Seas and meteorology, local meteorological conditions. And the removal processes of rain, clouds and gravity, as I said before. And factors controlling dispersion of pollution are wind, stability of the atmosphere and subsidence. Wind you know, and stability of the atmosphere, I don't know, someone has already talked it to you. Otherwise, I will tell you briefly in next slide. And subsidence is the descent of air. Air coming from the top of the atmosphere to the surface. The movement of air. See, this is called temperature inversion. This is typical temperature profile. You have a decreasing temperature profile as a function of altitude. And here you have an increasing temperature. So this is called, this will lead to atmospheric stability. If you don't know, during tea time I can tell you. But only thing you have to remember is that when you have a temperature inversion, there will be no vertical mixing. It will be less, much less compared to this condition. Here, see the smoke plume is steadily going up. Typically, when you have a sunny day, then you will see this kind of a condition. And here, this is stopped area. So this cannot go more than the inversion there. It is a bar. You cannot go much. So, and the wind, effect of wind is dilution. If you have, this is an industrial area and this is an residential area. The smoke from this, even if you have an inversion layer, see it will get diluted when wind is 10 meter per second. But if wind is 5 meter per second, dilution is less than the whole area will be chopped. That is how the dispersion. And subsidence, as I said, is descent of air. And that also can block the vertical mixing of these particles. And there is a saying that solution to pollution is dilution. So these three, inversion and wind and subsidence, can affect your dispersion. So what you need to use if you want to study such a scenario-based dispersion model, where the difference between the two is that if you want to study long-range transport, you have to use a model, global, and then your resolution will be much larger. It can be 250 kilometer resolution. Every box you have data will be 200. It is grid size. We call it as a grid size. So 250 kilometers. And in this dispersion, simple dispersion model, you can have up to 1 kilometer or even less. So you can see the microscopic features. See one example of a dispersion model grid. This is a dispersion, typical dispersion model. If you have topography, in a global model you may not be able to see this topography. This is a three-dimensional structure. And you can describe area sources as well as line sources. See, that is an area source. This is a line source. And area source means if you have widespread biomass burning, or you are talking about a large number of industries at that place, then it is an area source. Line source is a national highway. You have a national highway, so the emission is coming from a line. Or you have an aircraft route from Bangalore to Chennai, you take between it will be a straight line. So that is also there. And see, this is the same thing for when inversion is weak. Whatever is the area sources you are getting from the surface can get transported or get dispersed to very high altitudes, up to 24 kilometers it can go. But then in inversion is strong, low level inversion is present, it will be blocked and at some point it will be stopped. And just see this one, you have emissions here. It's an industrial emission. And this is a typical condition of inversion. When you have temperature inversion, you don't have much solar heating of the surface. So the emission will be blocked. You will see it as a perfect straight line, that wherever the inversion is there, you cannot go up. So it will be mostly confined aerosol close to the surface. So if you measure in the afternoon session, you will be going to the lab and you will see the instruments to measure particles. And during winter season, you will, if they are showing you data on winter and you will see that during winter you have much more concentration of particles at the surface compared to summer. It is not actually because of emission. Emission is much more during winter. It is because of the vertical stability of the atmosphere. It is changing from summer to winter. Winter you have low level inversion. which trap this aerosol close to the surface. But during the summer, that is not the case. And this is example of coin sources. You have a few chimneys here, and the color is showing the age of the particle. See, days, this is 0 to 124 hours, is the range shown. Once you have an aged aerosol about 18 to 20 hours old, then you have this blue. Otherwise, initial emission is shown as white. So this is how a dispersion model give you the output, how the coin sources are getting dispersed to different areas. And in addition to this removal and source processes, you can also have transformation processes. That is important. Because one aerosol, once it is produced, it can change its characteristics after production. So one is growth humidity. I am sure you know what is relative humidity. So relative humidity, as a function of relative humidity, it can change. The particle can grow to large particles. And then coagulation is two particles colliding each other and becoming one large particle. Specifically, when they are in liquid phase, if two aerosols are colliding each other, it will form a bigger particle, single particle. So it can affect the size distribution, how the aerosol size is distributed as a function of size. That is very important in radiation. When you make assessment on aerosol or radiation, that is very important. Similarly, cloud processing. You have probably read that before writing, one cloud can undergo 4 to 9 cycles of condensation evaporation cycles. Because every cloud is not a raining cloud. So once a cloud forms, 4 to 9 times it can undergo evaporation condensation processes. So in that process, if you have condensation and evaporation process, the aerosol which acted as condensation nuclei will be released into the atmosphere. But as a different characteristic, its characteristics can change. So that is why we are including that also in the transformation process. And see the mechanical disintegration. Now I will tell you the production mechanism of this aerosol that may be helpful for you to understand the process. This is typical desert. It is produced and how it is moving around the world depending on the global circulation system. And one point you needed to notice, it is becoming airborne by the action of heat. And wind speed above 0.5 meter per second are capable of picking up and keeping air around the particle as large as 2 micrometers in size. 0.5 micrometer, 0.5 meter per second is a very small wind speed. You know, if you look outside, no leaf is moving, but the wind speed may be 0.5 meter per second. If you have that is sufficient to keep airborne a 2 micrometer size aerosol, which is quite large particle. And 0.1 micrometer particles are capable of traveling up to 5,000 kilometers from the source. You have seen this animation. How much it can actually go around the globe. And how you can calculate the source function. If you want to model, you have to put dust in the wind tunnel. This is small particles you are putting in the wind tunnel. The wind tunnel is usually used to design an aircraft structure. But if you keep it in a wind tunnel, you will see that how many particles are becoming airborne at different wind speeds. So you can calculate the production function. And large particles and small particles, they behave differently. You have a different source function for large particle and small particle. You can very well imagine. Large particle, very less number of particles will be produced. But small particle, a large number of particles will be produced even in a small, even if you expose to a small wind speed. And now coming to sea salt aerosol, how it is produced from the ocean. Somebody asked me a question before. So this is how it is produced from ocean. Sea salt aerosol mostly produced because of wave radiation at high wind speed and the ocean is covered with white cap. See the waves is trapping large number of air inside this, and then it forms bubbles. So in different steps you can see that bubbles are formed at the ocean surface, and when the bubble breaks, it injects few particles, large particles, because water rushing into this bubble cavity, it will create an unstable condition and this jet is formed. And that is called jet droplet. And then when the film breaks, you have a large number of small droplets called film droplets. And then you have a very high speed, like above 10 meters per second. Then you have this direct spray also. And air mixes into water and forms clouds of bubbles. This is amplified picture of what I have shown before. And this is bubble, typical bubble. And few number of film droplets and jet droplets are formed every time a bubble breaks and sea spray. And one important thing to note is that the threshold wind speed needed for sea salt production is 3 meters per second compared to 0.5 meters per second over desert. Can you tell why? Because over ocean you need to overcome the surface tension also. Over desert region, 0.5 meter per second wind is sufficient to produce particles from the desert, but over ocean you have a surface tension. You cannot just remove a particle, you need to have some process which creates particles. So because of surface tension you need more energy to produce particles. So your threshold wind speed over ocean is 3 meters per second, and for land it is only 0.5 meters per second. And see the organic eruption, sulfur dioxide, large amount of sulfur dioxide is injected when you have an organic eruption. And this is an example of how an organic eruption suddenly increases the atmospheric aerosol concentration, and then it will take about 45 months to come back to normal. This sudden increase is what you have seen in the transmissions before. And man-made industrial emissions are mostly coming from industrial emissions, automobiles, all mostly contribute to industrial emission. Any human activity can produce anthropogenic aerosols. And biomass burning, automobiles, it can create black carbon, which has a significant role in climate modification because of its absorption character. As I said, absorption means it's warming. It is not a good news as far as climate is concerned. It will complement into carbon dioxide warming. And its absorption properties depends on the amount of graphite in that. So this kind of burning is not a complete burning compared to diesel. If you are using in a diesel engine and burn, that is kind of much more complete burning than this. So when you produce aerosol from burning, this kind of burning, then it will not have much graphite content. That is one issue which you have to remember. So it may not be completely absorbing, right? Because graphite is 100% absorbing. If you illuminate a medium with the graphite, you won't get anything back because most of the radiation will be absorbed. But in Indian conditions, mostly it is coming from biomass burning or agricultural burning. Graphitic content is not that high, so that is why you have the 77% absorption and 22% scattering. So that scattering is coming from the substances which are not actually absorbing. And any burning of this kind, it can, or automobiles, can emit carbon-containing aerosol, and it is in general called the carbonaceous aerosol. So it can be organic carbon or black carbon. The organic carbon is not absorbing, it is actually a scattering type of aerosol. See the color here. It is an automobile emission and this is a biomass burning emission. Biomass burning emission mostly is organically due to organic carbon, and this is black carbon. and you see the color is all white. White color means it is scattering. If it was absorbing, all the wavelengths will be absorbed and you will see it as black. So that is why this is black and this is white. And here the ratio of black carbon to organic carbon varies by source. And biomass burning fire result in aerosol, which is organic component. So that will actually lead into cooling, not warming. But in case of automobiles, you will definitely lead into warming. So that is more important. And if you really see how aerosol affect climate, it can affect climate directly or indirectly. So directly it can affect climate by scattering returning sunlight back to space and also absorbing sunlight, that is in visible region. And indirectly it can affect by modifying the properties and lifetime of clouds. So aerosol can act as cloud condensation nuclei, and I will tell you how it affects the properties and lifetime of clouds. And because of these two processes, aerosols are capable of affecting the climate system. And we typically use a parameter aerosol radiative OC, which is defined as the change in radiation both shortwave and longwave due to the presence of aerosol. That is defined as aerosol radiative. And this you probably know the fundamental extinction law. So if you eliminate one small medium from one side and if you whatever you take from the other side of the medium, you can calculate using the extinction law. I is equal to I0 exponential minus extinction coefficient into distance, the thickness of the medium. So any basic physics or climate science textbook, you will see this law and more details about this. And from this, you can calculate, you can get the definition of extinction coefficient. Extinction represents the loss of energy from an incident radiation due to the combined system, scattering and absorption. So this is the simplest form you can calculate. If you are eliminating the medium with I0, what you can get on the other side is I0 exponential minus extinction coefficient into thickness of the medium. This Lambert law. And from this, you will be able to calculate the optical depth which I am telling from the beginning. So, if you integrate this extinction coefficient from surface of the earth to the top of the earth, that is, you are integrating extinction coefficient along a vertical column of unit cross section, and the height along the height, then it is called the optical depth. So, it is the combined atmospheric effect. This is one of the most fundamental parameters to study aerosol effect on climate. You will be extensively using in your tutorials this term. So why it is important is because it is representative of the vertical column. So you don't have to actually divide the atmosphere into different layers. So this helps you to define the entire atmospheric effect, because in many applications you don't need to know what is happening inside the atmosphere. So what you want to know is, you know that how much radiation is there available at the top of the atmosphere, that is coming from the sun. Simple Planck function you can calculate it. But then your interest will be how much is arriving at the surface of the earth. That is one thing which you will need to do. And how much is lost in the atmosphere, entire atmospheric column, due to scattering and absorption. So for that purpose, this is very useful, because you can define boundaries, surface of the earth, top of the atmosphere. So you have two boundaries, and whatever is happening in between is defined optical depth. So it is the optical depth is a measure of the combined effect of scattering and absorption in a particular form. So major contributors for extinction in the atmosphere, which is cloud filling, are aerosol and air molecules. There are two components, aerosols and air molecules, that we need to remember for tutorial, because we need to calculate air molecular effect and aerosol effect. separately to study the aerosol effect, because you will get extinction coefficient, but then you need to separate this into two separate entities. And there are three parameters very much relevant to climate. That is optical depth, which I have defined here. And then single scattering albedo, I will tell you in 2 minutes, and scattering phase function. So this is how extinction coefficient is integrated from surface to the top of the atmosphere. And single scattering albedo is defined as the ratio of scattering to extinction. That is fraction of energy lost due to scattering is called single scattering albedo. So when I say black carbon, if you are illuminating a medium dominated with the black carbon aerosol, single scattering albedo is 0.82 means, or 0.8 means 80% is scattering contribution and 20% is absorption. That is what it indicates. And for black carbon, I said 77% is absorbing and 23% is scattering. So in that case, single scattering albedo is 20.23. So that is how it is defined. When you have completely absorbing particles, then single scattering albedo is 0. And if it is a completely scattering aerosol, then single scattering albedo is 1. So these two parameters you need to remember carefully, because that will be useful in your tutorial session. And phase function is a little more complicated, so we won't be able to use the phase function. But I will tell you briefly about scattering phase function. Scattering phase function defines the angular distribution of scattering. So this is a polar diagram. This is your incident beam. A small particle here shown as white is illuminated from one side, and this is how the scattering pattern looks like. This is 90 degree to the incident beam, and this is the same direction of the incident beam. So if you want to calculate the scattering angle, so this direction is 0, backward direction is 180 degree, and perpendicular is 90 or 270. So when you see that when particle size r is much less compared to the wavelength of radiation, you have both forward and backward scattering same. Scattering equally scattered in the forward direction and backward direction. And then when particle size is comparable to that of wavelength, you can see that more in the forward direction and less in the backward direction. So when I say backward direction and forward direction, see, if you take the sun and earth scenario, when you have more scattering in the forward direction, that means more energy is coming towards the earth's surface, and the less energy is going back to the space. So that is the relevance here as far as climate is concerned. And very large particle, when the particle size is much larger than wavelength, see the scattering pattern gets very complex. So you get secondary lobes, and calculating this phase function will be very difficult. And this is very large particle like cloud droplets or sea salt dust particles, which is very large. Then you get this kind of phase function. So we are not going into the phase function for tutorial session. We are only using optical depth. I will use optical depth and single scattering albedo, and assume atmosphere as a single column, and will tell you how to get the impact climate, its effect on radiation, surface reaching, or the energy escaping to space, how to calculate using those two parameters. And this is the simple representation of direct radiative forcing for short-wave radiation less than 4 micrometer. You have two processes here, scattering and absorption. So simple terms, most simple terms, in direct radiative forcing below 4 micrometer, this is short-wave radiation, that is solar radiation, that is sunlight in simple terms. You have a reduction of solar radiation at the surface, which I said the popular term dimming, surface dimming. So when you have aerosol which is scattering and absorbing, you have a large reduction of solar radiation at the Earth's surface. And because of scattering, you have an increased radiation going back to space. So you are increasing the reflectance of the planet. So both are happening. See, three things are happening. You are scattering some energy back to space, you are reducing some energy reaching the surface. So what will happen to the difference between the two? It will be absorbed in the atmosphere. So whatever is reduced here, it will lead to a cooling of the Earth's surface, and whatever is going back to space, it will lead to overall cooling of the Earth's atmospheric system, and whatever is trapped in here or absorbed in here, that will lead to warming, atmospheric warming. That is the simple message I want to tell you. And this is little more complicated. We are not dealing with long wave radiation today. But in long wave, mostly you have absorption. Because I have shown you the single scattering envelope here. You can see that even completely scattering aerosol like the sulfate, for example, sea salt and sulfate, every aerosol type is highly absorbing in the IR. Because IR region, you have mostly absorption. And your source is here. Surface, that's sigma T raised to 4. Stefan's Boltzmann law, you can use to calculate how much of the energy comes to here in a simple term. And the effect of absorption is a decrease in the Earth radiation. How much is coming from Earth and going back to space is called as outgoing long wave radiation, or in simple form OLR in satellite if you are using satellite data. And there will be a decrease in the OLR when you have a lot of absorbing force in the atmosphere. Most of the aerosols are absorbing in the infrared. So that will lead to a reduced OLR. And if you want to calculate simple terms for a scattering aerosol, this is the equation which you can derive per se today evening. You may not be able to derive it today, as or now, but by today evening after the tutorial session, you will be able to derive this equation. This simple equation will give you the aerosol radiative. S is solar constant and atmospheric transmittance, a fraction of sky cover and clouds, and surface reflection, backscatter fraction, and scattering. This is what this scattering fraction you will get from single scattering envelope. The moment I will give you optical level and scattering, single scattering envelope, you will be able to calculate the rest. And how to calculate, that is the purpose of the tutorial. And you will be able to derive. This is a purely scattering aerosol. You will see that this will lead to cooling of the Earth atmospheric system. And for an absorbing aerosol, it is an actually and for an absorbing aerosol, it is also scattering, so you can assume that this is a scattering and absorbing medium. Then you can also calculate aerosol radiative effect as a function of aerosol data. It is a kind of linear function, and you plot for different absorption conditions. Single scattering envelope 1 means a completely scattering condition, and single scattering envelope 0.9 means it is slightly absorbing, and 0.8 is even more absorbing. So this is the plot you will get, and all the parameters are known. If you know aerosol optical depth and single scattering envelope, aerosol optical depth is the column, atmospheric column integrated extinction coefficient that I needed to give you, and single scattering envelope, that is fraction of scattering to extinction, I needed to give you. If you know these two parameters, you can make an impact assessment of aerosol radiation. And how those two are measured, that also you will see in the lab session. So when you go to the lab, which is in the same floor, you will be able to see how to measure aerosol optical depth. and how to measure single scattering albedo. Both will be combustion and and indirect effect. Indirect effect is because of its ability to act as cloud condensation. So simple terms you can say more aerosol and more cloud droplets. That was the original belief. Because when you have more aerosol, you will have more cloud droplets because water will contain some of these particles and form cloud condensation and condensation. So cloud droplets. And hence cloud reflect more sunlight. So that result is cooling. This is an old concept. So I will tell you also what is happening in current scenario. And I am using sea salt as an example for cloud condensation. Okay. There are so many aerosol types which can act as cloud condensation. And more aerosol, you have a given number of aerosol, and that can inhibit the growth of cloud droplets because you have the water vapor availability is safe. For a given amount of water vapor, you have assumed two scenarios. One scenario you have a large amount of aerosol. One scenario you don't have less number of aerosols. So, in the first scenario, all the available water vapor will be shared among all aerosols. So, you have a large number of small cloud droplets. And in second scenario, you have a small number of large cloud droplets. So, the probability of raining is more when you have a large particles. Where with small particle it has to undergo several processes like collision, balance, etc. Then only it will rain. But large particle, because of its gravity effect, it will start moving downward and it collide with other particle and trigger rain. So because of that, it can inhibit the rain. So in that case, you have a prolonged cloud lifetime. You have more number of aerosol, you have prolonged cloud lifetime. Lifetime will be more means possibility of getting evaporated is much larger. It may never rain. If you have a less number of particles, it may rain. Probability of raining is more. And here, when you have more aerosol and more cloud droplets, scattering effects are more. So the net effect is cooling. And see the example of aerosol cloud and how it can act as cloud condensation nuclei. This is the emission from industries, sulfate aerosol, which is a very good cloud condensation nuclei. So you have the particle coming here and sunlight is heating the surface of the air and the particles are carried into higher altitudes. So then see it is going up and then it will trigger the rain. Because why it has to be carried up is it has to be cooled. So that adiabatic cooling will lead it to condensation and then it will start raining. And then this is the current scenario. See, you have one type of aerosol here and biomass burning aerosol here. This is coming from industry and this is coming from biomass burning. So you will see that here you have the rain, but here you don't have rain. The reason is the biomass burning aerosol, it is highly absorbing aerosol. So industrial aerosols are it can act as condensation and they are very good. We call it hydrophobic and hydrophic. So this can act as cloud condensation nuclei, so it will rain. But here, what is happening is biomass burning aerosols are heating the atmosphere. So because of intense heating of biomass burning aerosols here, it is not raining in this region. I can show you many examples. See the example of a volcanic eruption here. As I said, volcanic eruption inject large amount of sulfate aerosol in the atmosphere that can act as cloud condensation. So this sulfate aerosol, this is a trajectory of sulfate aerosol. You see the clouds forming along the trajectory of this. The reason is these particles from this volcano. So anthropogenic sulfate emission will increase the cloud cover by 15 to. This is actually volcanic effect. Increase the cloud cover by 5 to 10%. If you take a satellite picture and calculate cloud cover, it is increased by 5 to 10% because of this volcano. At the same time, this is an example of Amazon rainforest. We have intense forest fires here. See, you have clouds everywhere except over the region where you have smoke. What is happening here is you have a large amount of smoke from biomass burning here, and because of the intense warming by black carbon, clouds get evaporated. So evaporation of clouds is one effect, and aerosol acting as cloud condensation is another effect. So these are all two competing mechanisms. So which one is dominating, that depends on the net effect. And also changes in the state of mixing also have an effect on ability of aerosol to act as cloud condensation. I have shown you in the previous animation, when you have two types of aerosol, one is dust and one is smoke, and you have industrial emission also, they get mixed and its ability to act as condensation nuclei will be affected. And this is one important example, very interesting example of how black carbon can evaporate clouds. Maybe beyond the scope of this course, so I will skip that. And this is the climate effect. Both the direct and indirect effect lead to cooling of the atmosphere. This is the hypothesis. Aerosol cooling may affect the global warming. There is an old scenario. It's not the current scenario, but it's not a proven. Also, it is an old scenario. Aerosol cooling, first of all, the net effect of aerosol is cooling or warming is still not known. We needed to make a much more assessment. Even in the latest IISc report, there is no clear inference that what is the effect of different types of aerosol, because database is not adequate. It's a new field of research and database is not enough to make a complete assessment. And only what we can say is most important aerosol in climate cooling are industrial aerosol, salt aerosol, and natural sulfate which is coming from the ocean. I did not tell you, but phytoplankton in the ocean can use sulfate and it can form sulfate aerosol, that is also considered part of the natural sulfate. And most important aerosol which can form climate are man-made black carbon aerosol and natural dust. Both, you can see the color itself is brown and black, so that itself shows that it is highly absorbing, because whatever wavelength is illuminated on that medium is getting absorbed, so you see it as very much black. And the question is this: aerosol cools or not? Answer is not yet known, but this much we can tell you. The question of aerosol, whether aerosol cool or warm, the planet depends on the relative contribution of various species which constitute the aerosol. And aerosol with significant absorption aerosol into black carbon can have a net warming effect and complement greenhouse warming. That much is known. And an aerosol with the significant scattering aerosol, for example, sulfate or sea salt, and then can have a net cooling effect and offset partly the greenhouse warming. This is also known. So that is all we know. We don't know more about that. But we cannot say a conclusive statement whether aerosol cools or warms the planet. And now coming to the effect of radiation. Let us think what happened to shortwave radiation at the top of the atmosphere. This is also a useful thing for your tutorial in the afternoon, to think how much energy will reach the surface of the earth from the top of the atmosphere. The one possibility is that it can be absorbed by the atmosphere. What are the absorbing species in the atmosphere? Absorbing gases and absorption due to aerosol. And it can get reflected by clouds, particles, and air molecule back to space. Because air molecules are much smaller than wavelength of incident radiation, that is solar light, it will lead it to Raleigh's scattering. And particles are comparable in size, so it will undergo rescattering. And because of this, some energy is reflected back to space. And part of the energy can be transmitted to the surface, where it can be absorbed, reflected upward into the atmosphere. Because if you are talking about an area with the snow, a large amount of radiation will be reflected back to the atmosphere and finally we leave the atmosphere. And some of this may be absorbed by the atmosphere and some may be transmitted through the atmosphere back to space. So this is one possibility. And if it is longer radiation, what will happen? Whatever radiation is getting absorbed by the Earth's surface will lead to warming of the surface, and then it will re-emit. So Earth's surface emits longer radiation, and some of this radiation is directly through the atmosphere to space, thus cooling the planet. And some is absorbed by gases and clouds in the atmosphere, and atmospheric gases and clouds emit longer radiation in all directions. It is not like scattering phase function I have shown you. The long wave emission is all directions, it will emit. And the atmosphere's long wave emission downward on the surface of the Earth, and the atmosphere's long wave emission upward joins that from the surface escaping is cooling the planet. So this is the summary of what happens. Long wave radiation we are not handling today, only short wave radiation, because it is simpler than this. Here we need to worry about all absorption times and all. In short wave radiation we will use only the window wavelengths where you don't have any molecular absorption. That will simplify the problem. So this is a typical example of a simple radiation model. You have the sun illuminating the top of the atmosphere, we call it as layer 1. Divide the atmosphere into different layers. Every atmospheric layer is having a different property. When I say property, most important is optical depth, single scattering flow, and phase function. And you have a surface reflectance of which depends on what type of surface you are talking about. About 6% for ocean and 25% for land. It can be 80 or 90% if it is a snow or ice. So it depends on that. But we will be handling is this kind of a condition where you have an overhead sun here and you are illuminating the top of the atmosphere with the solar constant. And your objective is to calculate how much energy is reaching the surface and how much is lost due to scattering and absorption in the atmosphere and how much is going back to space. And either you can assume surface is black so that no energy is going back, or you can assume that it is 6% proportion and 0.1 for land. Whichever way you want to assume. Once you assume surface refractance is greater than 0, that the surface is non-black, you are complicating the problem further. And take a simple example of clear sky and short wave radiation, and you have incident like this one and only one layer. Then from Lambert clear law, you know that I is equal to I0 exponential minus extinction coefficient in length. So where here m is the slant path optical depth to vertical optical depth. Because you are considering that sun is on the overhead, in the overhead position, your m is equal to 1. Because you don't have a slant path, you are talking about a vertical beam from the sun to the surface of the earth. And you have transmittance, which is transmitted energy divided by extended energy. And you can calculate from this equation to divide, take this I0 to the left side, I by I0 is equal to minus 16. M is 1. So this, if you integrate extinction coefficient over a vertical column of the atmosphere, what you get is optical depth. So that means exponential of minus optical depth will give you the transmittance. And major scatterites are air molecules and aerosols. Air molecules are responsible for Rayleigh scattering, and the aerosols are responsible for E scattering. And major absorbers in the atmosphere are ozone, water vapor, CO2, like that. We will ignore this. We will consider cloud-free conditions in the afternoon tutorial session, and then only air molecules and aerosols will be considered. First we will see surface is black, and then we will go for non-black surfaces also. And this is the optical that I have shown you. And if we define the following parameters, the transmittance of the atmosphere due to Raleigh's calculation we define as PR. Then in the same way, we can define transmittance to aerosol, and processes are scattering and absorption, and molecular absorption is also TM. So the total transmittance will be the product of all three. That will give you how much energy is coming at the surface of the earth. I know that many of you did not understand what I am talking about. I will be talking in detail in the afternoon tutorial session also. So that is okay. But if you know approximately what I am talking about, that is sufficient for now. Only thing you have to remember is the total transmittance of the direct solar beam passing through the atmosphere is product of three separate transmittances we will be calculating. That is the only point I want you to remember. And this is your top of the atmosphere, and this is the surface of the earth. You know how much is coming because this is solar constant and transmittance is T. You have already calculated, which is exponential of minus optical depth. Simply you take your mobile phone and calculate transmittance, you get T. So you multiply that with this, you will get how much is coming at the surface of the earth. And in our case, if you take I0 is equal to 1 degree, then ground reaching radiation I will be equal to transmittance of the atmosphere. And the balance, the difference between the two, that is I0 minus I0 into T. So you take I0 outside, I0 into 1 minus 1 is lost in the atmosphere due to scattering and absorption. Because you have I0 here, I0 into transmittance reaches the surface. So the difference between the two is what is lost in the atmosphere. So the difference between the two is simply 1 minus transmittance equal to I0 is 1 unit. If not, I0 is equal to solar constant. So S0 into 1 minus transmittance. And this is called diffuse radiation. If you don't have absorption here, it is only because of scattering if this is happening. Then whatever is lost is diffuse radiation. Because you have two components in the surface reaching radiation. One is direct component and diffuse component. Direct component is the direct beam reaching the surface, and diffuse component is coming because of scattering. If you look away from the sun, what you see, you still see the light. It is not that sky is very much dark. You can see sky is illuminated. That is because of diffuse radiation. And if you take a simple atmosphere with only molecules, so the Rayleigh scattering is the main process. Diffuse radiation with Rayleigh scattering is equally 1 minus TR, the same I have explained. And in this way, you will be able to calculate the complete thing which I will explain to you. This is the final radiation model you will be able to derive in this manner. So, because by showing in a slide representation, you may not get the idea. So, it is better to write it in the board, so that I will do in the afternoon. But this is the final atmosphere, which you can calculate with the help of a calculator, how much direct radiation reaching at the surface, diffuse radiation reaching the surface, total scattered in the atmosphere, total absorbed in the atmosphere, total reflected back to space. We will not consider this angle, we will consider sun in the overhead position. So that we will do in the afternoon. So what I will do in the next lecture is a little more recent development in this field. So I guess with this background, you will be able to follow what I am going to tell in the next presentation. Mostly it will be the recent issues. I am going to talk different issues and give you what is the current status. And second half of next presentation, I will tell about few instruments which we use to measure, that you will actually see the instrument in the lab. As I said, A batch of 10 will go to the lab and rest of the people will sit here and do tutorial. When they return in about half an hour, the next 10 will go. Like that, we will organize it into 4 groups. Thank you. We will meet at 11:30.
You showed a 3D box with black carbon and clouds, I think. There's a box with clouds in it, and he was talking about simulations that are maybe too complicated. Can you show that again?